Okay, so I'm going to go over this CubeSat challenge and try to show some important points and make some suggestions. So first I'll talk about general considerations. Then I'll talk about pre-processing and feature selection, then algorithm design, and then training and testing. And this roughly follows the Jupyter notebooks that you were given to look at for the challenge. All right, so general considerations. First of all, ChatGPT is your friend. Use it to create new code quickly and phrase your queries well. I'll give some examples in the subsequent presentation, but this can definitely speed up your coding. Of course, you always have to verify whether ChatGPT is giving you what you really need, so you do need to understand the code that it gives you. But ChatGPT also often gives explanations, which can be very helpful, especially if you're just ramping up with Python. Okay, now, the goal of this challenge is to design an algorithm with high accuracy and low computation. So there are two objectives, high accuracy and low computation. So two possible strategies are start with a simple algorithm and improve the accuracy, or start with an accurate algorithm and decrease the computation. Now I can say that the notebooks that you were given, the two Jupyter notebooks, which we have here, ML, IPYNB, and CubeSat, these are two examples that show the extreme ends of algorithms. The Notebook 3 gives a very simple algorithm that underperforms, and the CubeSat gives a much more complicated algorithm that is probably too complicated. So you can start from the simple aspect and try to make it better, or you can start from the complicated and try to make it simpler. Generally, if you're doing a classical machine learning algorithm, you're going to have to do things to try to improve their performance. And generally, with a convolutional neural network, you'll have to think about ways to simplify. So now when you make choices in your model, do some preliminary calculations to evaluate trade-offs and make intelligent preliminary choices. You can calculate how complex or how processing intensive a model is going to be. So do those calculations, and then you can make intelligent choices about how to configure your model. Machine learning, deep learning, it's all about making choices. And you don't just want to make them randomly because you have limited time. You want to make choices that are based on sound intuition and sound reasoning. Next, streamline your test procedures. The faster you're testing, the more options you can explore. If you really want to do well in optimizing your algorithm, you're going to want to test a lot of different options because there are many, many options. So you want to have a procedure, a test procedure that's fast. And I'll talk about that more in the subsequent slides. Now, also look at your training diagnostics and understand what they're telling you. When you do training, you'll get certain feedbacks from the algorithm, especially with training of neural networks, and make sure that what you're seeing makes sense. Don't just train and look at the final number. See if what you're doing makes sense. So I'll talk more about that also in the rest of the slides. All right, so first let's talk about pre-processing and feature selection. Okay. Now, reducing the input data can greatly reduce the processing time, and this holds no matter what type of algorithm you use. However, you don't want to reduce the input data too much. If you looked at Notebook 3, you have seen an instance where the data was reduced too much. If I go there, you can see this. In this case, you had the downscaling to target size 64 by 64. Now, the original image was 512 by 512. This is far more than a 10 times reduction in data. So this is overkill. Now, downscaling may be a good idea, but you want to balance that against reducing your performance. Grayscaling also is combining channels, which reduces the amount of input data. I'll say a little bit more about that in a minute. Okay, so you want to keep the input data that gives the most relevant information. Now, the question is, your image has 3 channels, R, G, and B, 3 colors. Do you really need all 3 channels? Are you really getting different information from those 3 channels? That's something you can look at by looking at some of the images. Now, can you reduce the resolution? That was the downscaling. So, like I said, 512 to 64 is overkill. But maybe you can get away with 512 to 256, perhaps. And that's something that really can reduce the computation. If I reduce 512 to 256, then I'm reducing my data by a factor of 4 because it's a square, right? Now, can you get away with taking a section of the picture instead of the whole picture? When you do downsampling, you are reducing the resolution, so stars will tend to get more fuzzy. However, if you take less of the picture, you can retain the resolution, but with less data. Now, the problem with this is that you may just keep the wrong section of the picture. If you have missing data and you happen to choose a corner that doesn't have missing data, this could be a problem. So you can reduce your picture intelligently by taking only stripes or corners. And I'll give an example of that below. Now, originally we have the entire image, which is a lot of data. 512 times 512 is a big number. Now, do you really need all that data? What about just recording the distribution of intensities? Is that enough information to distinguish between the different types of images? So that's something to take a look at. Now, if you do that, you may take quantiles. Quantile is basically the rank, the value at 10%, 20%, 30%, etc. I'll show you later what that means. Okay. Now, to answer these questions, you should look at the data. Don't just start off doing something. Take a look at the data, see what it looks like, see what characteristics it has, and then make choices accordingly. Now, so these are ChatGPT codes that I put into ChatGPT to generate exploratory code. And you can see that my queries are very specific. And in fact, I got this code and I ran it out of the box, and it worked fine. So if we just read this, I have a NumPy file, trainimages.npy, which is the name of my training images file. And this contains images, and another NumPy file, trainlabels.npy, that contains corresponding labels. There are 5 different labels. I want to select 1,000 images and their corresponding labels. The images should be balanced among the 5 classes. I want to store the images in selectedimages.npy and the corresponding labels in selectedlabels.npy. Now, as I said, my query was specific enough so that I could simply copy and paste the code from ChatGPT, and it ran out of the box. All right, so I'm reducing the number of images because I want to examine by hand. I don't want to do an automated algorithm yet, so I want to work with fewer images. I want to display these images to see their characteristics. So this was my second query. I have a file selectedimages.npy, which was up here, that contains several images. Each image belongs to one of 5 classes. The corresponding classes are in selectedlabels.npy. I want a Python program that will randomly select one image of each type and display them side by side in a row of 5 images. Again, I copied this code and ran it out of the box. Okay, so and here is the result of that code. And then what I did was I modified the code so that it only showed one channel. It only showed channel 0. There are 3 channels, channel 0, 1, and 2, corresponding to R, G, and B. All right, so this is all the data, and then this is the data from channel 0. Now, if you look at the configuration of these pictures relative to the classification, you're really not missing that much if you just take one channel, right? This one here is supposed to be blurry, and this one is also blurry. right? This one, and I guess this is, I'm not sure what this is. I think this is noisy. This is noisy. This is corrupted. This is missing data. This is blurry. And then this is good. This is the priority, okay? And you can see that those different classes still can be identified by just taking one channel. Now, one channel is 1/3 of the data out of the box. So you might consider just taking one channel. Now, I looked at channel 0. You can look at the other two channels and see if one of the other ones are better. Now, one thing that also looking at the data really brings out is that there's some problem with the labeling of these images. This image is labeled as blurry, but there's missing data as well. You can see there's missing data here. So that is an issue. It's not an issue with the algorithm. It's actually an issue with the data itself. So I'll come back to that as well. So for instance, your algorithm may misclassify, but in fact, because the labeling is defective, it may actually be picking up the right features, but it still counts as misclassifying because the labeling itself is faulty. Right? So that's something to take care of. All right. So another thing that I did was I mentioned that you could take just part of the image. So this is not downsampling. I take my original image and I just take 4 corners. I take a corner here, a corner here, a corner here, and sorry, let me go back up, and a corner here. Okay, and those are 100 by 100 corners. So this is 512 by 512. So the 100 by 100 corner here, 100 by 100 corner here, etc. Okay, and that does greatly reduce the image. It says by 75%. But I think it's even more than that. It's far more than 75%. So that's an error. But and you can see also that this noisy class still looks noisy. This corrupted still looks corrupted. This missing data still has missing data. This blurry still looks blurry, and the priority still looks good. So now these images look bigger, but in fact it's the same resolution. You're just seeing it blown up. It's the same resolution. So in some ways, this may be better than doing downsampling because you maintain the resolution, but you also reduce the data. Now, as I said, this is really extreme reduction in data because instead of 512 by 512, basically you have 200 by 200, which is quite a bit less. Now, 100 by 100 might be too little, so you might start with 200 by 200. But that's going to reduce your data. It's going to reduce your computation time. And so the question is, does it reduce your accuracy also? So that's what you would have to estimate. Okay. So that's another idea for reducing your input data. All right. Now you also have a choice of converting your image into a completely different format. You could do something like Fourier transform or something like this, but as we'll see later, most classical machine learning algorithms do not take images as input because they don't preserve spatial relative position. So typically, classical machine learning algorithms take flattened data, linear data. Now, if you're taking linear data, why not just take the intensity profile, the intensity histogram? Okay, so what I did here was I typed this into ChatGPT. I said I have a single channel image, so I decided just to use one channel of my image. I want to plot the histogram of intensities as a subplot within an array of plots. I want to set the x-axis to run from 0 to 99th percent quantile. 99th quantile. That means that the 99th quantile is the data value such that 99% of the data is less than that. Why did I choose the 99th quantile? Because there are some extreme outliers. I want to get rid of those. I don't really care about those. I only care about 99% of the data, which will give me the characteristics that I want to see. Okay. I also want to mark the deciles on the x-axis. So the deciles are the percentiles at 10, 20, 30, 40, etc. All right, so you can see the different classes and you can see their histograms and they have quite different characteristics. You can tell visually the difference. For instance, this corrupted class, you can see that there's a lot of 0, which is actually missing data. So this is another case where you have missing data and corrupted. And then you have a lot of pixels that have relatively high intensity, and then nothing in the middle. Okay, so then this one here also, this one has missing data, lots of pixels with 0. Okay, that's an indication of missing data. So these are going to be easy to identify just by looking at the histogram of intensities. Now, the histogram of intensities is far less data than the original image. It depends on the spacing of your histogram bars. You could even get 1,000 histogram bars, and that would be far less than 512 by 512. So this is an enormous reduction in data, and what that will give you is also an enormous reduction in processing. But like I said, you can still pretty much tell the difference between these. I suppose that this one and this one may be a little bit difficult, but you can see that these are more closely spaced together here. But this one here, this one has this blurry one. Sorry, I don't know if this is blurry or noisy, so I'll have to look at that. But you can see that that it starts here. There are not many pixels with very low very low intensity. I think actually this one should be noisy, and then this one is blurry. So you can distinguish those. So it looks like the difficult one is going to be the difference between this blurry and the priority. And look, you can see the priority also has some missing data. So no, I guess it doesn't have missing data. It actually has data there. That's not missing data. Yeah, but I think this is definitely missing data, and this is definitely missing data. All right. So one possibility is convert your images into intensities, and that really can possibly greatly reduce your computation without decreasing your performance that much or at all. Okay. All right, so that's about pre-processing. Second, we'll talk about algorithm design. Now, this is here I say algorithm design, really I mean the data model. So typically, you have two main choices, conventional machine learning or deep learning. All right, and in the notebooks that you were given, Notebook 3 and Notebook 4, Notebook 3 was a conventional machine learning algorithm, and Notebook 4 was a deep learning algorithm. So we'll go over those and talk about the trade-offs and talk about what you might do to make these options perform well without too much computation time. So first, let's look at the conventional machine learning algorithm. That's an example of that was the Notebook 3, which we had here, and the algorithm they actually used was this one called stochastic gradient descent. And you can see here that they did do a flattening. They changed the image into a linear array and removed the area structure. Here they did grayscaling, and as I said, I think that's questionable. You probably can improve that just by taking a single channel. And with conventional machine learning, because it's not as intelligent as deep learning, you need to put in more of your smarts. You need to give it data that it can recognize. So intelligent pre-processing and feature selection are key for conventional machine learning. Okay. So when you do conventional machine learning, you probably don't want to use the entire image, because conventional machine learning typically uses flattened input that does not preserve spatial relationships. So you can use the intensity distribution, the histograms that I showed, and use quantiles. Now you can use hundreds or thousands of quantiles. You can take the value at 0.5%, the value at 1%, the value at 1.5%, etc. Certainly you want to include 0 as one of your categories, because for images with missing data, you can right away spot one of those if there's a whole bunch of zeros in the image. So when I say distribution quantiles, what I'm talking about is this back here. You convert your image into a histogram. And like I said, you'd probably want to use more bars than this instead of just, I think this is like 20, 25 or the default. You'd want to use more bars than this. And then it would be good to convert it into quantiles. And then you can run that through a machine learning algorithm. Or you could actually run that through a deep learning algorithm as well. You could run it through a neural network if you wanted. But that's a way to reduce your data and possibly make things run a lot faster. All right. Now, let's think about the nature of the images that we have. We're trying to classify images of stars. Now, there are some easy ones to classify, the corrupted and the missing data. Those are easy. The ones that are hard are the blurry, noisy, and priority. Those are difficult. Now, what's the difference between a blurry star and a good image of a star? Well, the edge is blurry, right? If you look at the edges here, if you compare these have sharp edges of these bright dots, sharp edges. But these have blurry edges, so they're more graded, they're more gradual. Okay, so one thing you might want to look at is the edges that appear in the image. So like edge detection filters, like the Sobel operator, canny edge detection, and Laplacian variance. These are 3 examples. So like I said, the good quality or the priority images will have sharper edges, and that may be a way to distinguish the priority images from the others. Now, these edge detection filters require that you install OpenCV. Because that's a special package in Python to do edge detection. Now, once you did the edge detection, what you'd have to do is something like what you do with the regular image is convert that into a distribution and take quantiles. But this might give more information than the regular image. And something you can do is you can actually ask ChatGPT to apply one of these operations to your images and compare and see what kind of distribution you get for these. And if you can tell the difference between distributions for the 5 different classes. Right? So you might consider that as a possibility for pre-processing. Okay. There are also algorithms within OpenCV that can identify stars and pick them out. You could write an algorithm using OpenCV that would identify perhaps 10 or 20 stars and put bounding boxes around them, and then you could run another algorithm on those selected stars. So there's a lot of possibilities you can do using OpenCV. So OpenCV enables you to do with the image things that you might do by hand, but it automates them and also takes relatively less computation time. Right. Now, some machine learning algorithms run much faster than others. For instance, logistic regression is very fast. So you can describe the problem to ChatGPT and get suggestions. So you can tell ChatGPT what you're trying to do. You're trying to classify images of stars. The stars look something like this. I want to use a machine learning algorithm. Tell me what algorithm will run fastest. You can ask ChatGPT things like this. And we'll give suggestions. Now, you shouldn't take that as absolute truth. But usually when ChatGPT gives suggestions, it also gives reasons. So that's good input. Right. Now, another thing you might consider is use more than one algorithm. Some algorithms may be good for some classes, and some might be good for others. So you can run these algorithms in sequence. First, you do one algorithm, and then you can run another algorithm on the images that don't get classified during the first algorithm, right? So you could do them in sequence, or you could do them in parallel. You can run multiple algorithms on the same data and then do like a majority vote. That's something like random forest, right, where you do multiple classifications and then take a majority vote. But you can be creative here. You don't just have to use a single algorithm. You can combine them. And if you're using conventional machine learning, these algorithms run fairly fast. So quite possibly you can do several of these for the same computational cost that you could do a single deep learning or neural network. Okay, so let's take a look at Notebook 3 and see what could be improved there. I've already touched on some of these points, right? In Notebook 3, these were the pre-processing steps: grayscaling, normalizing, downscaling, and flattening. So why not take a single channel instead of grayscaling? That actually doesn't save much computational time, but it saves some. You can say every little bit helps. Okay. Now, as I said, downscaling may help, but this was extreme downscaling, way too much. Okay. And flattening is necessary because conventional machine learning does not preserve spatial relations. Okay. Now, machine learning uses the notebook uses the stochastic gradient descent method. So the question is, what is this method? I actually didn't know what it was, so I had to look it up. So I went to the documentation, and I found out that it's actually not a different method. It's just a different way of training the model. That the default stochastic gradient descent model is support vector machine. That's the default, the linear with a linear kernel. But you can also use stochastic gradient descent to train a logistic regression model. So there's several options here for that you can set for stochastic gradient descent that will change the performance. And for instance, a loss function, a penalty function like L1 or L2. So don't just use your algorithm out of the box. Explore the options and think about which option might be better for your particular application here. Okay. All right, so that was the considerations for classical machine learning. Let's think about deep learning or deep learning algorithm design. Now, deep learning means a neural network, and for images, convolutional neural network is the natural choice. Because convolutional neural network does look at areas, and it scans images just like human beings scan images and looks at small pieces to identify local features. So I think that this is really kind of a no-brainer. You would not use a recurrent neural network. You would not use LSTM. You would not use adversarial. I think CNN is the natural choice for the type of neural network you would use. All right, but within CNN, there's a lot of additional choices. How many layers? For each layer, what size kernel do you use? I'm assuming you know something about convolutional neural networks. If you don't, you can certainly find lots of references online. How many feature maps do you use? What stride do you use? Now, this is not used in CubeCatNet, but it really may be helpful because it's a way to greatly reduce computation without reducing a lot of without getting rid of a lot of data, still preserving a lot of data. So pooling, should you use max pooling or average pooling? And then activation function. Now, activation function also in this case, because we're trying to make an algorithm that performs fast, ReLU is probably the way you want to go. It's much faster than the other activation functions. So you have lots of choices to make. You want to make some intelligent choices. So you should do some preliminary computations. So I show how that works in a minute. Now, to better understand the effect of number of layers, kernel size, number of feature maps, see this simulation. This is a really nice simulation. This one does the digit classification. If I draw a digit here, this is an exploded view of a convolutional neural network that classifies the three. And you can see here's the original image down here, and it has 1, 2, 3, 4, 5, 6, 7 layers. I think this is actually this looks like a max pooling here. Yeah, this is downsampling. So this is downsampling. It's not max pooling. It's just downsampling. Right. So these are the feature maps at the first level. 1, 2, 3, 4, 5, 6 feature maps, and then here they're downsampled. So really, we have 1, 2. I think that's still a square. So we have 1, 2 feature maps, and then then this is flattened, and then we have a fully connected here. Looks like you got 2 fully connected layers here. That one goes there, and that one goes there. So 2 fully connected layers, and then the final classification. Now, what I see here is that this type of picture, this type of figure, the things that we're trying to identify are somewhat more complicated than the images that we're trying to look at. We're just trying to look at clear or blurry images of individual stars. And this only has 1, 2 convolutional layers. whereas I think that the one that is in CubeSat SAT was 4 convolutional layers. So that tells me that there might be too many convolutional layers. There's also only 7, it looks like 6 feature maps here. And this has excellent performance. So you may want to consider the number of feature maps and the number of layers, reducing those, and reducing them in a way that's not going to reduce the performance. So I'll talk more about that also. I like this this image that really shows what's going on. I can go in here. I can look at one of these pixels here, and this tells me this is. So I think you can see on the left there, that square, that's telling me what is being input from the original image, and then there's the filter on the right. That's the same thing as the convolutional kernel. So you can see it's a, what's that, 1, 2, 3, 4, 5 by 5 kernel, looking at the value of that image of that pixel there. And here the output is not very large because the filter does not match the input very well. Okay. So we can find a case where, if you look here for a bright pixel there, you can see the input image and the filter match quite well. The input image is bright where the filter is bright, so that's why you're getting a fairly bright output. Okay. Okay. So let's go back to my presentation. So I would recommend playing around with this and seeing how these feature maps and the downsampling. So if I look at downsampling here, so looks like here it downsampled by, I guess a factor of 2. Looks like a factor of 2. Seeing how that works. So they use downsampling instead of max pooling. All right, so that's something to look at. All right, now here is the CubeSat design, and this was in Notebook 4, and you can see we have 1, 2, 3, 4 convolutional layers. After each convolutional layers, there's a max pooling, and then finally there's what's called a global average pooling, which basically collapses the spatial part of the layer output here to give 128 different values, and then the 128 is fully connected to the dense 5, right? So I wrote these steps over here. What this here is a 3 by 3 kernel, and there's 16 feature maps. So if I compare this with this one has a 5 by 5 kernel and only has 6 feature maps, right? So, and then this, like I said, this is max pooling 2, 2. It's going to reduce the size of the image by 2. By taking the maximum value of the ones in a 2 by 2 region, and we do the same thing repeatedly. So the question is this 3 by 3 choice good? Is this 2 by 2 choice good? Why would we use these choices instead of something else? Now, one thing about 3 by 3 kernels is they evaluate very quickly. In the neural network here, we have 5 by 5 kernels, and that has 25 pixels in the, can I get that here? Let's see, if I can, I'll move it around. There we go. If you take a look at that, whoops, let's do it here. All right, there's 5 by 5, that's 25 pixels you need to evaluate. Now, for 3 by 3, you only have 9 pixels. That's only 1/3. So the evaluation time is much less, but the area that's covered is much smaller. So you're looking at features within a 3 by 3 sub area of this bigger image. Now the question is, do you really need 16 features for 3 by 3 pixels? That seems like a lot of features. So I would really question whether you need 16 features here for this 3 by 3. 3 by 3 I think is a good choice because it does evaluate quickly, and it's a good way to scan the entire image in a fairly quick way. Also, max pooling I think is good because max pooling is picking out within a 2 by 2 subregion where you have the largest signal. right? So it's kind of homing in where you're getting your strongest signal within a 2x2 area. So I think that's a good idea, but I'm not sure if 2 is the best choice here. Since this is 3x3, I would tend to think this should also be 3x3. So that's something that might also be explored. Okay, so I would explore reducing the number of features and also perhaps increasing the max pooling. Now here is a place where you can put stride in as well instead of max pooling, or in addition to max pooling. Stride will reduce the number of matches. Instead of trying to match every single 3x3 patch in this image, the stride will skip. It will look at one 3x3 patch. It will look at one 3x3 patch, and then it will skip one pixel, and then it will look at another 3x3 patch, and then skip another pixel, and so on. So that means you're greatly reducing the number of patches you're looking at, reducing the computation quite a bit, but still, in fact, looking at the entire image. So I would consider including stride here in addition to max pooling. Instead of or in addition to. So those are things that you can do to reduce the amount of computation and possibly not reduce the accuracy. All right, now as I said, what you should do is you should calculate how much computation is being required for each operation. So let me, I'll go through one of these in detail. This one here is describing the first layer. The first layer here was this 3x3 kernel with 16 features. And it's acting on an image, 512 by 512 image with 3 channels. So in fact, instead of having just a 3x3 as this has here, this is looking at square blocks of the image. In the case of CubeSat, it's looking at 3x3 blocks for 3 different channels. So it's not just 3x3. In fact, it's 3x3x3 or 27. So that adds to the computation, right? So you have a 3x3 kernel. You have 16 features on 512 by 512 by 3 input. Okay. So when you do computer calculations for computer complexity, typically you count how many multiply accumulates. Multiply accumulates means you multiply 2 numbers and add it with another number. And that's really all that this is doing when you're doing this convolution. You're multiplying and accumulating. So every time I do a single kernel, single 3x3x3 block within the image, that's 3x3x3 multiply accumulates, and that's per kernel calculation. Now, since I have 16 features, I'm doing 16 kernel calculations per location. And the number of locations is 512 minus 2 times 512 minus 2. Why minus 2? Because of the edges, because my 3x3 kernels can't go over the edges. Okay. Now, if I multiply all these numbers together, I get 112 million. So that's 112 million multiply accumulates for a single image. Now, that may seem like a lot, but modern processors can do, with 1 gigahertz or 2 gigahertz, can do 1 billion or 2 billion operations per second. So this is something like 1/10 of a second, which is still quite a bit if you're trying to do a lot of images. All right. Now, after you finish this calculation and obtain the feature maps, you're reducing them using max pooling. And as I said, I think max pooling is a good idea because it picks out the locations where you're getting your biggest signal, and then you can follow up on that in subsequent layers. So you're reducing the size of the layer. All right. Now, what about the next layer? The next layer, if you look back here, it's going to go there. Next layer was 3x3 kernel, still 32 features, but it's on a smaller image because we've done the max pooling. We've basically divided both the length and the width by 2, so the image is 4 times fewer pixels. However, I've also increased the number of feature maps. Right? So, and I have the number of feature map outputs increased. I also have more features on the input. I have 16 different features input instead of 3 channels to begin with. So if I do a similar calculation here, for each kernel calculation, for each 3x3 patch in the image, I'm going to get 3x3x16 multiply accumulates. Then I have 32 calculations per location for the 32 output feature maps. And then these are the number of locations. Again, I subtract 2 because of the edges. When I multiply this, I actually get about 3 times as much processing. So it's not the first layer that's causing me most of the problem, it's the second. And then if I do the third and the fourth, I'm getting similar amounts of processing. Then after that, after the fourth image where you have 128 features on 62 by 62 grid, you're collapsing the 62 by 62 into a single number. So you're greatly reducing the amount of data to 128. So what's going on here? Well, when you do these successive layers, this basically is looking at 3x3 patches. But this is looking at 3x3 patches of 3x3 patches. It's actually looking at a larger area. It's looking at multiples of these patches. And then this is looking at multiples of these patches. And this is looking at multiples of these patches. So basically, the different layers are looking at larger and larger areas. And what we'll see in a minute is I can actually show you what size of area that the convolutional neural network is looking at after these 4 layers. So it's looking at patches of a certain number of pixels by a certain number of pixels. I think it's 40 by 40, something like that. Now, in those 40 by 40 patches, it's basically identifying 128 different classes, the configurations of those 40 by 40 patches. Now, some of them might be blurry stars, some of them might be empty space, some of them might be something else, some of them might be noise. But what it's doing is it's counting the number of occurrences of these 128 different classes or features within the entire image. And then it's doing global average pooling. So that's, I had max pooling before. That's wrong. It's global average pooling. So it's really counting up the number of each of the 128 types. So in some ways, it's kind of like a histogram from what we did before, but it's a more sophisticated histogram. It's not just a histogram of the it's not just a histogram of the intensity. It's a histogram of these 128 features, which are much more complex. And then what it's doing then is a fully connected layer. So it's just trying to characterize the distribution of those classes into the 5 possible images that we have. So as I said, this is kind of similar to what you would do if you just took the image histogram and did 128 quantiles and ran a network on that. So the question I ask when I look at this is, do you really need so many features? And do you really need so many levels like this? Could you get away with fewer layers and maybe a larger kernel? It might be a larger kernel, but it would still look at large enough areas so that you could characterize different stars. So that's what I would ask. I would ask, can we use fewer layers and larger kernels? Can we do more? Can we do more of this this max pooling instead of 2 by 2? Do 3 by 3? Can we add some stride to reduce the calculation? Now, this is certainly a case where we have something quite complex, and we should be able to simplify it without sacrificing performance. Okay, so this is where the complexity comes in. These 3 layers have equal complexity. And if I got rid of one of these layers, that would greatly reduce the complexity. And as I mentioned before, if I cut down the number of input pixels by half, then all this would be cut by half. So I think almost certainly you can start with this and reduce the complexity. and without sacrificing performance. All right. So what's happening here is this is kind of a schematic of what happens when you do the max pooling. So each one of this small square here, this is a 3 by 3 square. Right. So that would be one convolutional kernel, one or kernel or filter, scanning the image. Now we scan across the image, so we do this 3 by 3, then we do the next 3 by 3, then we do the next 3 by 3, and so on. So here I have 1, 2, 3, 4, 3 by 3 evaluations. Now, when you do the max pooling, it's looking at, it's taking the results from these 4 kernel outputs and finding the best one. So it's actually looking at information from a 4 by 4 region. Right. So after the max pooling, I can say the square of influence around each node has side 4. Right. Each result of each output of that max pooling really is looking at 4 by 4 squares of original pixels. And then you can continue, like this one here. You can see that after the max pooling, the max pooled results are spaced by 2. So if I take 3 cases of these max pooled results, those are the blue dots, right? Then I take 3 by, then I take this one here, this one here, this one here. So I've got these 4 by 4 regions of influence. So I've got 3 of those, and that gives me this square here. But then when I do the max pooling on the next layer, I'm going to take 4 of these larger squares. Each one of these larger squares has 1, 2, 3, 4, 5, 6, 7, 8. I'm going to take 4 of these larger squares, and so I'm going to take this square here. It's a little hard to see. This square here, and this square here. Okay. So I have a larger region of influence. So each time I go to the next layer, I'm increasing my region of influence. Now I have on the next slide, this is actually a live spreadsheet. If you get the presentation, you can go here and click in the spreadsheet. Should be able to. And you can see the different aspects here. There's image size, max pool size, kernel size, image depth, and number of feature maps. Okay. In fact, image depth is the same as number of feature maps staggered by 1. And then here I have the calculation for the mega max, the million multiply accumulates per second. And here's the number of parameters. So you can look at these formulas that I put in. This is the same formula I explained in this slide. And then this is showing the distance between nodes. So you can see that we end up with a 46 by 46 square around each node. All right, so let me go back to my slideshow. All right, so a 46 by 46 square around each node. And how many nodes do we have? Well, if we look here, after the max pooling, we have 30 by 30 locations. So you have 30 by 30 locations where each location is looking at, what was it, 46 by 46 square? And in that 46 by 46 squared, it's trying to match 128 different patterns. And then what it does with the global average pooling is it's counting the frequency of those different patterns. And then it's going to do conventional multi-layer perceptron to convert those frequencies into classification of the 5 types of images. Very similar to what I mentioned earlier when you take a histogram and you take the quantiles, and you could use that directly in the same way with a multi-layer perceptron. All right. So I hope that gives some insight into the things that you can try with a convolutional neural network. I do think there's quite a bit of room for improvement in the network that's there already in notebook number 4. All right, so let's go on to training and testing. So efficient training is the key to algorithm development. Your training pipeline should be configured so that you can quickly evaluate and compare algorithms' performance. You want to try a lot of different options, and so you want to be able to do that quickly. So if we do the conventional machine learning algorithms, they typically train very quickly. So there should be no problem with using the entire training set. However, you might want to do something about the class imbalance. If you look at notebook 3, again, that was a very bad algorithm, but you can see in the confusion matrix, many of the blurry, corrupt, missing data, noisy instances that were actually blurry, corrupt, missing data, or noisy were misclassified as priority. And the reason for that is that there were many more priority than there were of anything else. So the classification was tend to bias towards priority. And that's going to happen if you have unbalanced classes. So you might consider balancing your classes in your machine learning algorithm training, but I don't think it's going to be a big issue for algorithms with high accuracy, because you're not going to get large amounts of misclassified instances like you would here. Another thing I do think you need to watch out for is something I mentioned before. There's some ambiguity with the labels. There's some images that have both missing data and noisy, or both missing data and corrupt. So you might want to look at your confusion matrix. You might want to look at the actual images that are misclassified and see if there was some problem with those images. And maybe that your algorithm is fine, but the labeling is problematic. Okay, so always look at your data, look at your results, look and see what's actually going on with the actual images. I would say, by the way, also that the confusion matrix is much more informative than the accuracy or F1 score, because it's telling you which of the different classes are being confused, and then you can address that particular confusion. For instance, here you can see that most of the corrupt are classified correctly. So that one's taken care of, right? So the ones that are worse are the blurry and noisy. Those are the ones that are really being confused. So those are the ones you need to address. And we could see that visually, that the blurry and noisy images do look much more like priority, right? But the confusion matrix can tell you that. All right. So again, if you're looking at CNN models that require several minutes for training, you consider training on a reduced data set with balanced classes. Now, actually, this code up here that I gave before, this code here creates a reduced data set with balanced classes, right? So this has 5 labels. This is 1,000 images with 200 images of each class. So you might create a training set like this, a reduced training set, and do some preliminary training with a reduced training set. I do encourage you to do that if your training is taking a long time, because you do want to evaluate a lot of different algorithms. Okay, so if you do that, make sure you train the models multiple times to make sure your results are consistent. Like you may get different accuracies for different instances. You may get 0.92, 0.95, 0.91, something like that. So you don't want to, you want to make sure that you have a good estimate. So if you get 0.92, 0.91, 0.95, and another algorithm has 0.96, 0.97, 0.998, then you know that the second algorithm is better, right? So you're just trying to compare different algorithms. You're not trying to get an exact number for the accuracy of your algorithm. So if you're just comparing algorithms, you don't care about getting the exact accuracy. You can use a reduced training set that can go faster. Because certainly you want to balance here. If you can train a model within a minute, that's fine. Just do it on the entire training set. But if it's taking a couple hours, you certainly want to reduce the complexity, reduce the amount of data in your training set. Now, once you've narrowed down to 3 or 4 models, then you can run the full training set on those, right? Now, when you're doing training, look at your training progress. So if I go here to the, not this one, I want to go to the CubeSat. So look at the training progress here. All right, this is doing what you expect it to do. The accuracy is improving, the loss is steadily decreasing. And here it kind of starts jumping around, right? Here we have 9959, 9962, 9983, 9978, 9942 is actually going down a little bit here, so it's kind of stabilized here. I don't think that means it's less accurate. It just means that these accuracy numbers there's some randomness in there. You can't expect the accuracy number to be exact. It's going to vary depending on some randomness. Okay, so just pay attention to that. I don't think that these differences are significant. All right, so make sure that your training progress is doing something like this. Now, in this particular case, they don't validate after each epoch. They only validate at the end. But make sure that your validation is consistent with the results that you get from training, right? If it's a lot different, that means that something is wrong. So if I look down here at the confusion matrix for validation, you can see how many wrong instances there were. There are only 5 wrong instances out of however many total data images there were. You can calculate what the accuracy was in this case. So this accuracy is consistent with the accuracy that you got from your training. So always cross-check. Always ask yourself, do these numbers make sense? And like I said, if you're getting accuracies that are bouncing around, if you're getting accuracy here that does not check out with the accuracy of your validation set, then don't keep going. Figure out what's wrong. If you can't build right results on wrong foundation. Your foundation has to be solid. So if something is wrong, make sure you understand what's going wrong. Okay, so as I said, if your validation accuracy is very different from your final training accuracy, you need to investigate why. If it's a lot bigger or a lot smaller, you need to understand why that is. Okay, now for final testing, you do need to run the final notebook on your algorithm. So if we look at the final notebook quickly, so here it says, in this hackathon, you'll use this notebook to evaluate the performance of your machine learning pipeline. So here when it's talking about pipeline, it's not talking about your training procedure. It's talking about the pre-processing and the model in your final algorithm. So that's what it's talking about here. And here you have these different evaluations. So you have to run these functions on your code and get these outputs, right? You need to get the confusion matrix. You need to get these values here. I will tell you that the most important values are the evaluation time and the accuracy, and the confusion matrix. Well, the accuracy and F1 score, confusion matrix, all pretty much the same thing. The confusion matrix is more detailed, but accuracy and F1 score are probably going to be very similar because the classes are not that unbalanced. All right, so these are the most important things: the evaluation time, accuracy, and F1 score. These other things are useful to look at for implementation. Your code size, most of the time the code size is going to be very small, so that's not an issue. The memory usage, well, that's going to depend on the device that you use, so that's a secondary importance. All right, so let me see if I covered all the bases, and I think we're about done. All right, so the 2 most important measures are model performance and evaluation time. Memory usage will adapt to the device, and the code sizes, even for complicated neural networks, are relatively small. And I think that's all. Thanks for listening, and have fun with the hackathon.